Hello, and welcome back to Mechanochemistry Discussions. This seminar series is hosted by NSF-funded Center for Mechanochemical Controlled Chemistry, or CMCC. My name is Mateusz Marianski. I'm one of the center's investigators. As always, the goal of this seminar series is to bring our community together. The seminar streams live on the third Thursday of every month at 11 a.m. Eastern, and it's also available to watch anytime on the YouTube channel. Also on YouTube, you will find all previous speakers that participated in the series, and I encourage you to check them out. We also have some excellent speakers planned for the following months, and we hope that you'll join us for all of them. Before we get started, a few quick thank yous. First, Dr. James Batias, the Center's Director, Jennifer Belzik, the Center's Administrative Coordinator, and two CMC students without whom the seminar would not happen, Katie Floyd and Ryan Kwok. Please do continue to follow us on YouTube channel at CMCC Mechanochemistry Discussions. And before we start, a few quick guidelines. First, the seminar is being recorded. If you have any questions, you can either email them to us at cmccdiscussions@gmail.com, or you can post them directly into the YouTube channel. Either way, they'll be propagated to the speaker at the end of the seminar. Without further ado, it is my pleasure to welcome today's speaker, Professor Daniel Tabor from Texas A&M University. Daniel Tabor received his Bachelor of Science in Chemistry from the University of Texas at Austin in 2011, where he was Beckman Scholar and did 2 years of research with Professor John Stanton. He then attended the University of Wisconsin-Madison and completed his PhD in Ned Sibert's group. His research focused on developing efficient theoretical models for the vibrational spectroscopy of cold clusters and molecules. From 2016 to 19, he was a postdoc with Alan Asperow-Guzik at Harvard University, where his research focused on computer-aided materials design, mainly working in the areas of energy generation and storage. In the fall of 2019, Daniel joined the Department of Chemistry faculty at Texas A&M University as an assistant professor of chemistry. His research group focuses on designing new functional organic materials, developing methods for accelerating the prediction and assignment of complex spectra, and accelerating materials and reaction discovery with scientific machine learning techniques. He was named a Texas A&M Institute of Data Center Career Initiative Fellow in 2021, a Cultural Scholar in 2023, and Montauk, Texas A&M Center for Teaching Excellence Scholar in 2023. It is my pleasure to welcome Professor Tabor to Mechanochemistry Discussions.
Hi, everyone. I'm Daniel Tabor, and I'm an assistant professor in theoretical and computational chemistry at Texas A&M University. And in this talk, I'm going to talk about a couple different collaborative efforts that are going on within the Center for Mechanochemistry. The talk title is a little long, but I promise we'll be able to unpack all of these things throughout the presentation. So I'll be talking about our fully computational work on identifying mechanochemically accelerated reactions through a combination of high-throughput screening, machine learning models, and simplified physical models. And this is a collaborative work between my group at Texas A&M and the Mariansky group at Hunter College. So let's start with the baseline model we're going to have for chemical reactions throughout the talk. So in freshman chemistry, we learn the basic profile that exists for a given chemical reaction. So here we have NO2 plus CO converting to NO plus CO2. And a good fraction of general chemistry is focused on computing the equilibrium constant of this reaction that you can know from basically evaluating some kind of energy difference between the reactants and products. But another substantial question in chemistry is, will the chemical reaction actually happen in everyday conditions? And that's connected to how high is the barrier for the reaction. So in general, reactions with higher barriers happen slower, and reactions with lower barriers happen more quickly. Now, what's traced out here is a topologically correct profile for what happens here. Some people will call this a reaction coordinate or reaction path. Often when people are analyzing these things, they will directly only look at what are known as the critical points on here. So you'll look at the relative energy of the reactants, the transition state, and the products, and you can build models that'll estimate rates that happen from those quantities. Now, one other thing that is really common in chemistry, if you flip 30 more pages in this tome of a textbook, you'll find this figure where you have a default reaction without any catalyst present that's relatively high. And then the introduction of a catalyst lowers the barrier by lowering the transition state, often by some complex multi-step mechanism that requires several intermediate steps, but the overall effective barrier is lower for the system. So our group focuses on essentially using force as a catalyst in some sense to speed up chemical reactions. But there are a few other things that you need to keep in mind as we do these searches. What's plotted here are 1D reaction profiles. There's only one coordinate down here that's happening. But for almost any chemical reaction, you're going to have a lot of atoms moving around. And so it reminds me of in Back to the Future when Doc tells Marty that he's not thinking fourth dimensionally. In our case, we need to be thinking 3n minus 6 or 3n minus 7 dimensionally. And so I can't plot in that many dimensions. But for instance, you can think about a reaction path happening on a multi-dimensional surface. And what we're basically trying to do here is we're trying to use external forces, stresses, things like that, to essentially find pathways with lower effective barriers that exist in the system. Now, how do we find reaction barriers in chemical reactions? That's actually something that's received a lot of intense development from the theoretical and computational chemistry community. And one of the most popular methods for finding reaction barriers is this family of methods known as nudged elastic band. And so this is just a pictorial representation for how this method works. What's plotted here in the dark colors background is the contour map of the potential energy surface on these two dimensions. It's essentially just like reading a topographic map on a map. And what's in white here is the minimum energy pathway that will trace you through this potential energy. That's a key quantity as you're estimating the rates that reactions are going to happen. However, you don't know this whole surface in advance. And so the question is, how do you efficiently find this pathway? And what's roughly illustrated here is the mechanism by which this family of methods works, where you basically have starting guesses, and then if you couple this with some calculus, you can essentially trace yourself towards approximate locations on the reaction path and ultimately find this point right here, which is that transition state structure and transition state energy. Now, I don't want to go into all the mathematical details of what's going on here, but the key idea here is that you need access to being able to calculate the energy of your system at any time or at any point in space. You need to be able to take the first derivative of that energy in any direction. So you have to be able to evaluate gradients of your system. And then it's super helpful if you can also evaluate the curvature or second derivatives or Hessian of your system as you're doing this. So this really speeds up the process, and it's going to motivate the choice of methods that we have as we do our searches here. So in the center, essentially what we're trying to do is figure out at the microscopic or more accurately nanoscopic length scale, how can we modulate reaction barriers with external forces? In general, I would say that I'm most interested in lowering reaction barriers. But in general, one could also change the pathway for a chemical reaction if there are multiple potential products. And so this is all done at the atomic or molecular scale. Now, most of the experiments that we have access to are here at the macro scale. So in this series, you've certainly heard about talks of ball mills. That's one of the most common reactors that's used in these systems. And all of those forces are happening on what we would call the macro scale. And so the question is, how are we going to be able to bridge this gap? How are we going to be able to take our predictions at the atomic scale and translate them into design principles for what kinds of chemistry to do in the macro scale? Now, there are a lot of conditions that exist at the macro scale, and a lot of very careful experiments have been done in this area where you can get very different reaction outcomes depending on how you apply your external force, at what frequency or magnitude you apply it, what materials your system is made out of it as you're applying it. And then there are several other experimental parameters that you can have in these systems. So I'll just give a quick example of a few cases where you have definitely nonlinear effects in these systems. So here's a chemical reaction that was published earlier last year, where basically we're not looking at rate here, but we're looking just at the overall conversion percentage that exists. And with underlines, I'll sort of highlight some of the more interesting results that you get out of here. So in some cases, you'll have opposite behavior on whether or not you employ liquid-assisted grinding in the system versus neat milling. In some cases, you will see very different behavior by just changing the composition of what the ball is made up of in your ball mill, whether or not you use stainless steel or not. And in some cases, you can see extraordinarily large differences in conversion rate that's sort of paralleled on whether or not you use liquid-assisted grinding or not, basically based on what co-catalyst or catalyst you use in the system. And so there's a lot of complexity here. And so to understand what's going on at the macro scale, the center has actually also done some really careful experiments to probe individual chemical reactions at a time. And that motivates some of our search here. So basically what happened in this reaction is instead of looking at things in a ball mill, we actually, some of my colleagues in the center, looked at what happens on individual molecule events here. And the way that you do that is you don't use a ball mill, but instead you have basically a atomically thin tip that you're using to impose the forces. So you can essentially coat these tips, which are very tiny, with one kind of molecule. And then you can have the other molecule that it's going to be reacting with immobilized on the surface. This allows you to do very careful experiments where you know how much force or how much pressure you're applying. And then you can watch the chemical reaction conversion occur to understand what's going on at the single molecule level. So when you do that on these Diels-Alder reactions, you can essentially see how the conversion changes as a function of different forces. You can actually look at it over a series of different arrays here. And then you can collaborate with the same people that I'm collaborating with on this project to learn a little bit more about what's happening at the molecular level. So basically, here is that same style of reaction profile that you learn all the way in general chemistry. And what you can do essentially in a quantum chemistry package is you can apply external forces to your system and then resolve for what the minimum energy geometries are at your critical points. And so you can test how does the barrier change under different types of external force. So what Ryan in the Mariatsky group did here is essentially tested the effects of either doing hydrostatic style pressure on the system, as indicated by the arrows here, or on doing uniaxial stress on the system. And so I'll just highlight, I know there are a lot of numbers floating around here. The key numbers here is essentially that the reactants distort more than the transition state on the application of these external forces. And so if you distort the reactants more, they actually go up more in energy than the transition state does, that lowers the effective barrier of the system. And so here's an approximate first model to have if you're searching for other kinds of reactions that could be accelerated by external forces, pressures, stresses, etc. And so we have the following open questions. Basically, how general is this model? Can we optimize existing experiments to apply the principles of this model to already existing chemistry that we have? And then finally, can we search for novel experiments or new kinds of chemistry to do if this model works? Okay, so to test the generality of this model, we're going to do what I've been trained to do, which is to do a lot of calculations and start to do some data science on the problem. So a postdoc in my group, Mark Boyer, and a graduate student in my group, Sushin Chow, have been working on a good fraction of this work here. Essentially, what we did is we took the Diels-Alder reaction type and built a library of potential reactions that exist here. So what I have shown here are 5 out of the 12 types of Diels-Alder reactions that you typically see in the organic chemistry literature. And then what we did is we essentially attached different functional groups to either the diene or the dienophile here. And those are going to change the electronic structure of the system ever so slightly, either through electron donating or electron withdrawing effects. You also could have some steric effects here, if you're familiar with those things in organic chemistry. And then what we're going to do is we're going to try to build an automated version of this model that the Mariansky group built, essentially searching over the reaction paths and the transition states under these external forces and trying to find the best kinds of forces to put on these systems to accelerate the reaction. All right, so this library that they built has 1,856 reactions. That is a modest-sized library nowadays. But remember, we're also applying external forces to these systems. And there are a lot of directions that you can apply external forces. Remember to think 3n minus 7th dimensionally here. There are also different magnitudes that you can apply as well. And so we can have quite the combinatorial explosion of things that we need to do here. So to be able to get this to work in high throughput, we're going to rely on one of the emerging tools that's being used all across the theoretical chemistry community right now, which are machine learning potentials. So I'll just provide a quick summary of how these work and what the practical implication of that is for our research. So there are a lot of these out there. The one that we're using in this particular screening study is known as AIMNet-2. It's the sequel to AIMNet-1. And essentially the way that this works is that every single atom in the system is assigned a site energy, and then you sum over all of those site energies to get the total energy of your system. The cool thing about it is that you can also take whatever derivatives you want of the system to find geometries, find the curvature of potential energy surfaces, and things like that. And I just want to point out that there are a lot of these. So if you want to build on our results going forward with your own favorite potential, feel free to do so. So here are some results for AIMNet-1 for how well it works. So here's the sort of AIMNet prediction of the energy versus the DFT prediction of the energy. And then you can also look at how the forces look. And so in general, this is a model that can predict DFT quality results, which is the typical way you search for barriers and reaction energies at molecular mechanics level cost. So this is at least 2 orders of magnitude faster. This speed is what's needed to be able to do the high throughput search that we're doing here. So this is going to be the engine that we use for preliminary screening over the set, and then we can always confirm our leads with higher level calculations. You can sort of think of it as a validation procedure there. All right, so we'll be able to compute energies as quickly as we basically need them. But the question is, can we be wise about how we apply the external forces on the system as we try to steer it? And so here we're going to go through a little bit of the details on the model that our groups have been developing here. Okay, so here's our favorite little 1D reaction profile here. I'm highlighting the parts that we want to care about. We care about what's going on in the reactant, and we care about what's going on at the transition state. Now, the best force that you can apply to speed up the reaction is to push yourself directly up the reaction profile. That's going to be the optimal force to apply to the system. But this thing is curving all the way through space as it's happening. And we don't have the current ability to be able to just steer reactions wherever we want them to go. And so given those constraints that essentially we're going to be applying essentially a constant direction of force over the entire reaction path, the question is, can we get an estimate for what that optimal force is going to be by only looking locally in the reactants area and locally in the transition state area? So what we do here is we basically do a Taylor series expansion of the potential energy of the system at both the reactants and the transition state. And we truncate that at a second order. And then what we can do is we can estimate that if you apply an external force to the system, you'll be able to guess how far it's going to displace there by how stiff the potential is, how stiff the springs are in your system at those two places. And so that's all that the math that is happening here is saying. Now, what this basically means, I'll basically get to the punchline, is that we want to find a coordinate in our system that is very low frequency in the reactant complex, and it transforms to being a high frequency coordinate in your transition state. And we have a little bit of an illustration that helps with this. The basic idea is that if you have a loose spring in your reactant, that means that your force is doing more potential work for you whenever you translate it over to the stiffer spring that exists in the transition state. So you have a loose spring in your reactant that corresponds to a coordinate that's a stiffer spring in your product. And to a very simplified order, you can actually estimate the amount of work that you're able to do based on the ratio of how stiff those springs are to each other. Now, it turns out that searching for that direction is only exactly solvable if you're in like 2 dimensions or something. And so we've come up with some numerical approximations for being able to use some of the techniques that you learn, I don't know, like halfway through calculus to find numerical estimates of where to step. And we're going to do this in several potential dimensions and then test how it works. This is just an approximation for where to put the force. We then use all of the traditional transition state searching algorithms under these forces to actually find what's happening to the reaction profile. Okay, so we can basically make these force directions in this model directly analogous to a vibrational mode. So here's an example of one Diels-Alder reaction, and the arrows indicate sort of the optimal way of applying the forces for this particular situation. You then run still the full transition state search run like you would have before. You just have this external force being applied to the system as you're tracing out the reaction path here. So this really is still testing how it works over the full path. So we do all of our evaluations at the critical points to get initial guesses for what to do, but then we still trace out the entire reaction path and find out what the new effective barrier of the system is going to be. Okay, so does it work? At the end of the day, that's what you're here for. So here's an example of a reaction where we have essentially applied the Mariansky model in high throughput over a large space of reactions. And we find that even after doing all of the reaction path searching, that we see exactly what they had found in their original model. So you have a destabilization of the reactants here, and basically no change in your transition state distortion that exists here. That leads to a 2 kcal per mole improvement in the barrier here. Now, one thing to remember is that at 298 Kelvin, basically every 0.6 or so kcals per mole of improvement that you get to your barrier, you're going to get a factor of about 2.7 improvement on your rate. So this ends up being, a pretty good improvement on the rate. So this is for one specific example. I'm now going to show you a scatter plot for how it works over a portion of the reaction space that we looked at. So here is a sample of 95 of our reactions here that have 2,397 as of generating this slide yesterday. External force directions applied to it. And the force that we're applying is 0.6 piconewtons per atom in this case, which we believe is a realistic mimic of the magnitude of force that one could apply from these experiments. So the key thing here is that, remember, we were making an approximation to get initial searches. Then we're confirming how it looks when we trace out the full path. This is often what happens in high throughput screening, is that you have a lot of initial guesses, and then with higher level calculation, you end up narrowing your space of optimal candidates here. So any positives are good positives here. So if it's below this first red diagonal line here, that corresponds to an estimated 10x acceleration rate in the reaction rate. And if it's below this second red line right here, that means that it corresponds to a 100x speed up in reaction rate. And so we have several viable candidates for how to push these reactions over only the small space of 95 reactions to begin with. So we went basically from 4 or 5 reactions to now dozens of potential reactions that will be further candidates for higher level computational investigation or potentially experimental testing as well. Okay, so I think that we've adequately answered the first 2 questions that we posed to ourselves on this study. And so then the next question is, what are we going to do to design new molecules for this? And in this case, we're going to use some tools that our group has developed for some other applications. So about a year and a half ago, the first PhD in my group, Cheng Han, who's now at Los Alamos, he basically adapted this reinvent framework that had been developed in the drug design community to work well with essentially more expensive quantum chemistry calculations. And he had done this to design molecules that have their excited state energies that line up in the right spot. And this is actually a very modular and adaptable framework because all it's doing is designing molecules sort of in their graph-based representation. And then it uses reinforcement learning to get smarter and smarter over time. That's why, it starts off sort of mediocre and then gradually gets better and better at targeting molecules exactly where you want them to be. And so this is a plug and play algorithm that we can apply to the system, where essentially what we do is, instead of design molecules with their excited state energies in the right spot, we instead design them where, when you run this automated engine on the system, their predicted reaction barriers, when you add in the optimal external forces, have maximum change on this front. And we can add additional constraints to the system. We can essentially ban functional groups that you don't want. We can also add estimates of synthetic accessibility to the system as well as you're doing this. So that's work that's currently in progress right now. So there are still several things that we'd like to investigate further on this front, and that's always the great thing about science. You solve one problem and get 3 new ones. And so, right now we're basically looking at how well the approximate framework that we used here for the, I guess, physical chemistry folks in the audience, we're looking at how important are anharmonicities in the system. We're also looking at basically how sensitive these things are to the force that we actually apply. We picked one constant magnitude in this case, but very likely you have a distribution of force magnitudes on these systems. And then finally, we're looking at how sensitive these directions that we have are to what coordinate system we use. And that's kind of a theoretical chemistry sort of issue. So the other axis that I just want to give a brief plug to is some work that the whole center has been doing on developing what we call the CMCC DB. That literally stands for Center for Mechanical Control of Chemistry database. And this gets back to the fact that we have these macroscale conditions where you have behavior that is difficult to explain with simple models. And so to help make progress on this front, we're trying to collect all of this data in one centralized location. And to do this, we actually started with the open reaction database that was developed by the NSF Center for Computer-Aided Synthesis, or ORD. So what we did is we created a fork of their open source code, and we added specific fields that exist for mechanochemical reactions. And this is an active development effort. You can check it out here at this link right here. And it's also on the center's GitHub repository. But this is a living system where we're adding new database fields and subparameters fairly regularly as we learn more and more about all of the things that the mechanochemistry community as a whole is deciding needs to be reported. So this is to address both reproducibility concerns and also to give people like us enough data that we can start training models to predict the reactions of outcomes from macro scale parameters instead of just trying to build everything atoms up. So to summarize my talk, I presented some results from a collaborative study going on between our group and the Mariansky group at Hunter College on basically generalizing a model that had been successful in explaining some experiments and looking at a much broader chemical space and showing that that model holds quite well and that there are lots of reactions out there that are potentially acceleratable by external forces. We used a high quality machine learning potential to enable this high throughput search. It basically saved us a factor of about 100 on computational time here. And then the other thing that I advertised right at the end is that we have developed this open source database with a lot of help from information technology here at Texas A&M that has current experimental data from the mechanochemistry community and potentially future computational data as well. So with that, I'd like to thank our collaborators, Ryan and Mitesh, and the people in my group. Oh, I shouldn't circle myself. I should think about that. But Daniel Williams is very active on the database. Mark, Sushen, and Sharon are active on both the database and on this high throughput search. And then finally, I'd like to thank the NSF for funding the CCI, and I'm happy to answer any questions. Thank you.
Thank you very much, Daniel, for your presentation. I mean, that's very interesting work. So I have several questions, and there are several questions in the chat about your work. So let me ask a couple of questions here. So one of the motivation slides, you showed how complex the mechanochemical reaction environment is when you highlight the effect of the catalyst, of the lag, and material of a ball mill. Yet, what you're looking at here is a very simple reaction system composed of the diene and dienophile. Can you foresee a development of your method to include more complex reaction environment?
Yes. So I think that there are a few ways that one could start to leap between these different length scales. So one thing that could potentially be done is you could do the best way of putting it, you could do a sort of molecular mechanics or molecular dynamics level simulation of your system. And then you could have, or you could even do a quantum mechanics / molecular mechanics simulation, where you start to map the kinds of forces or other interactions that you get on your system, and then translate it over to the sort of implicit surrounding force model that we've developed here. If the tools get high throughput enough where you can just explicitly simulate the environment, I think that's also possible. You could essentially be running larger scale, like reactive molecular dynamics, maybe with some enhanced sampling or things like that on your system. So I definitely think that it's possible. I have seen some, not to draw too many analogies, but there have been some very interesting studies, I think, in the electrochemistry community, where people have started with simplified models of, say, external potentials on their reactions, and then over time you've been able to simulate actual electrodes interacting with your chemistry that's going on. I think that we'll probably realize a similar thing in our community as well.
Okay, the next question is, can you give any examples of activation volumes calculated from your method?
Okay, yes. So that's a great parallel question. Yeah, so everything that we're reporting here is an effective barrier height. That's one version of the language that you can have in the system. But the other way that you could do this is you can start to think about what other things have energy, units of energy. So you could either do force times distance, but the other thing that you can do is you can do pressure times volume, or pressure times delta volume that exists in your system. And so actually, your group is one of the experts on doing these kinds of calculations. And so I probably should have had it in the backup slide, but it is one of those downstream calculations that happens from our lead candidates, where you analyze it in terms of the activation volume concept. And it will certainly be in the final report of this work as well as we publish it. So sorry I don't have them today, but yes, they are calculatable within this framework.
So it's very good that you're actually on this slide and you have this plot here. So there are different effects on the force on your reagent. You can even increase the transition state or decrease the transition state energy. Have you done any chemical analysis, or what are the properties of your molecules in the system that would lead to the decrease of this and acceleration of the reaction? Is there anything in common between these points that are below the second red line?
Yes. So in some of the cases, these are the same reaction with two different, let's see, anytime it's a vertical bar on this axis, this is same reaction, two different forces accelerating it by the same amount. So in those cases, those, I guess by definition, have the same functional group in common with each other. We have noticed, although I have to I would have to pull up the details, but there are some cases where a common functional group on the dienophile has been found across a few different acceleration conditions. Now, I would argue over a space of 95 reactions that I'm not quite ready to plant my flag as that being a design principle. We need to, finish the 2,000 or so reactions before we can start to do some statistics on the system. There are a lot of other parallel things that we should do to confirm things as well. We should look at electron densities, potentially plot orbitals. We want all of the physical organic chemists along as allies as we draw these conclusions as well. So there's both at the informatics level, we do see some preliminary results that are in common. We're still working on the exact physical interpretation of those things, though.
Okay, and the last question is about the development of your CMCC reaction database. Is so how to add the how to update the database as it is right now, and how does I see the slide, but how does the update actually look? Is it actively developed right now? And is there the question is specifically that if there are new parameters that would like to be reported in the database, how to update the framework that would accept?
Yeah, so updating the framework, that'll be a development side update. So in general, we have a plan to release updates about every 3 to 4 months is sort of when that would be called the schema getting updated. So the way to request a new field there would be to give what's known as a pull request on our GitHub. That would probably be the easiest way, although you could also send either the center director or me an email about that. In terms of uploading data to the database, we've worked very hard on actually making it to where you just have to make an Excel spreadsheet of the data that you're uploading, and then it's a browse, upload your spreadsheet, then it checks for any inconsistencies or errors, and then it gets injected into the database. It actually gets injected into the developer side version of the database because at this point we are thinking about the best way to do, I guess, final checking of anything before it then gets synced with the live version. So there is a little bit of a time lag there, and we are actively thinking about ways of adding additional monitoring tools on top of that.
And there's actually one more question in the chat asking about clarification of the way that you're choosing the forces to accelerate the reaction. And specifically, the question is whether the forces the resulting optimal forces are tensile or compressive, and in general, how you arrive at them.
Okay, so the resulting forces are much closer to being compressive forces in the current framework that we're working on things.
And could you clarify a little bit more how you are choosing these forces?
Yes. So essentially, the way that we do it is we search over combinations of coordinates that exist at both the reactant and the reactant and the transition state. We then calculate what all of the frequencies are in each of those directions. And then we look for essentially a projection of, so whenever a molecule is vibrating, we're looking for essentially a maximal overlap of a low frequency direction in the reactant to a high frequency direction in the transition state. It sounds like it should be something that's just algebra, but it's not algebraic, unfortunately. It's because matrices don't commute with each other, is essentially the one way of thinking about why it doesn't work that way. So we do a numerical search, and it turns out that this appears to have several solutions in multiple dimensions. And so we take the first 12 solutions that we get out of this whenever we do that search.
Okay, I think these are all questions that are from the audience. So thank you very much, Daniel, for your presentation. Thank you very much once again for answering all questions.
Thank you, everyone.
And thank you, audience, for listening. Thank you, Professor Tabor, for outstanding presentation, and thank you very much for joining us. Just to remind you that all our previous speakers are available to watch anytime on our YouTube channel, and I encourage you to check them out. We also have some outstanding seminar speakers planned in the upcoming months, and we hope that you will join us for all of them.